So my request is, if you have any doubt, please send me your messages in the chat box. I will be looking into your chat box continuously while teaching. Okay. So before getting started with any topic, friends, let us discuss few points about teaching in chemistry and what are the things that we should keep in our mind when we are preparing for advanced IITJEE. Okay. We all know that chemistry has got three parts broadly. One is physical chemistry. Another one is organic chemistry. Right, inorganic chemistry. Okay. Now, what are the things that we should keep in our mind while preparing? Because chemistry is different from the other subjects because we have got three different branches which are sometimes related to each other, sometimes independent of each other. Okay. I will take up each branch of chemistry and what are the strategies that should keep in your mind and that you should follow to excel in that branch of chemistry we will discuss. Okay. So I'll take few minutes for this and after that we will start any topic and we'll discuss regarding it. Okay. Coming to the physical chemistry. See, if you want to do well in physical chemistry, first thing that you should keep in your mind is that only numericals. The physical chemistry can be learnt only through numericals. Always collect good number of problems which are having different concepts. And in each numerical, you should teach one concept to the students that you should not forget. Okay. So for physical chemistry, you can follow Atkins. And for numericals, you can collect the different numericals from the different materials, or Neeraj Kumar is there, or Narendra Avasthi is there. So many books are there, but from those books, you can collect the problems. You should have a bank of numerical problems in sequence. It is not just simply giving you a problem, and in each problem, you should teach the students one concept. Suppose imagine that in physical chemistry, PV is equal to nRT is there, imagine. And you are giving numericals. P is not given, V is given, N is given, R is given, T is given. In another numerical, V is not given. In another numerical, N. Like that, those substitution problems won't work. See, in each numerical, you should teach students one concept. Suppose imagine, take one example. If you take the Boyle's law, okay, what Boyle's law says that T is constant. Okay. The numerical is like this, that a person is selling the balloons. Generally, we see this in exhibitions. Okay. Where hydrogen balloons are sold and children are very much interested playing with these balloons. Imagine there is a rigid vessel, rigid container is there. And in this, the volume of this is 10 liters and 9 atmospheres of pressure is there. And using this, it is containing some hydrogen gas or helium gas because these balloons go up against to the gravity, right? So we want to fill up, each one is a 2 liters balloon and having 1 atmosphere pressure. And temperature is constant. Temperature is constant. Suppose, okay. When temperature is constant, from this container of 10 liters with the pressure 9 atmospheres, how many balloons that we can fill up? Suppose options are given like this: 45, 40, 35, 30. Okay. And this is a problem. And you're all into teaching field. Okay. Can you send me the answer? What is the answer for this question? What is the answer to this question? At constant temperature, there is a container is present, and the volume of that container is 10 liters, and inside it, it's 9 atmosphere pressure is there. It's filled with hydrogen gas. And we have to fill up balloons, each of them having the volume 2 liters and 1 atmosphere pressure. Please send me the answers to this question. What is the answer to this question? Okay. Please send me your answers in the chat box. Okay, why I am giving this example? Because when we are using PV is equal to P1 V1 is equal to P2 V2, which is nothing but Boyle's law. I think nobody is sending me any answers. Any answers, please? No? Okay. So what I wanted to tell you here is that, suppose generally most of the students, what they will do is 10 into 9. This is equal to n into 2 into 1 they will do. And n is equal to 45. Most of the students, they'll give the answer 45. Whereas the correct answer to this one is what? See, from this cylinder, the gas is not completely evacuated because the gases always move from high pressures to low pressure, right? So what you will get here is that 10 into 9, which is equal to, then in this, the pressure will be equal to the outside pressure, and after that, no gas is coming out. Then final pressure in the cylinder will be equal to 1 into 10. Then this will be plus n into 2 into 1. This will give you 90. Then n is equal to 80 by 2. The answer is only 40. So it means this is wrong. The students are directly using the formula without knowing the concept there. Behind every numerical, see that there is some concept is involved. What I am trying to tell you is that, see, directly if you are applying the formula, you are getting the wrong answer, but there is one concept involved in this. So like that, select the numericals in physical chemistry. In each numerical, you should be in a position to teach one concept in that. Okay. Now coming to the second part of the chemistry, that is organic chemistry. In organic chemistry, as far as advance is concerned, give more importance to the mechanisms and follow all advanced books and don't read the local books. Peter Sykes is very, very important book. You can, Peter Sykes, you can follow for the mechanisms. So in organic chemistry, concentrate more on mechanisms and also more on G. And the third one is the third part of the chemistry is inorganic chemistry. In inorganic chemistry is very much neglected branch of the chemistry. I should say that both by the teaching community as well as students, but we should not forget that inorganic chemistry has got the equal weightage to the physical as well as in organic chemistry. 33% of questions we will anyhow get in the advanced as well as mains examination from the inorganic chemistry also. So in inorganic chemistry, first we should consider that in inorganic chemistry, just like a GOC is very important for organic chemistry, in inorganic chemistry, the chemical bonding is very, very important. So give first importance to the chemical bonding. It is helpful to you in both organic as well as inorganic. So chemical bonding is very, very important. Concentrate more on the chemical bonding. Then you can solve any problem related to the inorganic chemistry if you're strong in the chemical bonding. Because everything related to inorganic chemistry we come across in the chemical bonding only. All basics will be there in the chemical bonding. Okay. So like that, you have to follow different strategies for these different branches of the chemistry. Let us revise that. In physical chemistry, just like it should be a physics, give more importance to the numericals, and you should have a bank and collection of the numericals, and all these numericals should teach some concept to the students. You should prepare your own numericals. You should have your own numericals. Okay. And second one, organic chemistry, as far as advance is concerned, give more importance to the mechanism. And in inorganic chemistry, if you're strong in chemical bonding, you can do any problem or any question in any group. Okay. Right. So you're all into teaching field. Let me ask you a simple question. Suppose, imagine carbon dioxide is there. Okay. Now, if your student is asking you that, sir, why always we are writing in every book, carbon dioxide structure is given like this only. Okay. So please, if you have anything to ask or anything to tell, please send me the message. Okay. So that I will understand. Please send me the message. Okay. Why only carbon dioxide should be written like this? Suppose if a student is telling that, sir, can't we write a carbon dioxide like this? Why only it should be written like this? What is the reason? That if I write like this, what's wrong with this? Any answers? If I write carbon dioxide structure like this, what's wrong with that? Why always we are writing like this? Why we are following this type of structure for carbon dioxide? As an example, if your student is asking this, what would be your answer? Can I write like this also? Why can't I write carbon dioxide structure like this? What's wrong with this structure? Why we are always writing this structure like this? Please send me your answers. I want this should be like an interaction. Any answers? My question is, suppose imagine your student is asking you that, sir, why carbon dioxide is always written like this? Why we should not write carbon dioxide structure like this? What is the reason? Please send me the message. I think your chat box is open. Hello? Okay. Yeah. So some setting problem is there. And I think now you can send the messages. Right. Yeah. Sorry, I'm sorry. It was disabled. I made it into. Now? See that, can you send me the messages? Yeah, good. Somebody is telling that dipole moment is 0. Good. Zero cannot, oxygen cannot form 4 bonds. See, Anilji, this is also wrong that according to the maximum covalency rule, that second period elements can form maximum of 4 bonds. There are cases in complexes where oxygen can form the 4 bonds. Carbon dioxide is carbon 4, so we are using the first formula. Okay, what about carbon monoxide? In carbon monoxide, carbon valency is not 4, but still it is existing. Octet of carbon is not complete. Carbon valence is 4, octet of carbon is not complete. Why I will put the 2 electrons? What's wrong with that? If put like this, total electrons are distributed like this. Octet is now completed because of chemical bonding and covalent bonding. Okay. Okay. Right. See, everybody has given their opinion, but the game is energy. Always remember that energy plays an important role in chemistry, in the stability of the different species there. Lesser the energy, more is the stability. and more the energy, lesser is the stability. We all know this. Suppose, imagine if you take the carbon dioxide, I'll tell you one concept that how to convince the students that why we are following certain structures for the given compound there. Suppose imagine for carbon dioxide, we all know that how do you write the LDS? LDS means what? Lewis dot structure. We know that chemical bonding is nothing but it is a force of attraction between two atoms or ions which is holding them together, right? Is it correct that chemical bonding is nothing but a force of attraction which is holding the atoms or ions together there? Okay. And chemical bonding is always an exothermic process and energy is released in a chemical bond formation. We also know that, okay? Now my question is that, listen to this. My question is that in between two atoms, only attraction forces are existing. First option. What I'm telling is that in between two atoms, only attraction forces are existing. Only attraction forces are existing. Are both attraction as well as the repulsions are existing, but attractions are dominating over the repulsions. Okay. Third one, what I'm saying is that both attractions as well as repulsions are present, but both of them are equal in a chemical bond. Fourth, all are possible. All are possible depending on the situation if they are telling. With what option you will go? Here is that I'm telling that simply everybody knows chemical bonding is a force of attraction between two atoms or two ions. Now I'm asking you that in a chemical bonding only attraction force is existing. Second option, both attraction and repulsions are existing, but attraction is greater than repulsion. Third one, both attraction and repulsions are existing and both of them are equal to each other. Fourth option, all are possible depending on the situation he is telling. With which option you will go with? You'll go with which option? Please. Carbon is less electronegative, carbon is central atom. Okay. Now my question is that why we should take up only the less electronegative atom as a central atom? That is my basic question. You are following some rules. Okay. Carbon is having less electronegativity, but why we should take only less electronegative atom as a central atom? That is my question. What is the reason behind that? What is the reason behind that? Now, I think now you can send. Both attractions and repulsions. Okay, both attractions and repulsions. Both this is there in both the options. First is there, second and third options are telling both at equilibrium. Yes, correct. This is correct that both attraction and repulsion are existing between the atoms. So most of the students will be under the misconception that only attraction forces are existing between the atoms, whereas it is not so. The thing here is that imagine if you take the energy profile of repulsions are more if central atom is more electronegative. Achha. You are saying that repulsions are more if central atom is more electronegative. Suggest best books for physical, organic, inorganic, and advanced level. Okay, sir, I will do this at the end of this discussion, or meanwhile our discussions, I will tell you. I've already told you that physical chemistry, Atkins, you can follow. For organic, Peter Sykes. For inorganic, J.D. Lee's wonderful book. J.D. Lee, and another one is Miesler. There is one book is there, Miesler. This is also a wonderful book. Miesler, J.D. Lee is there. For J.D. Lee, both inorganic, for inorganic chemistry, both of them are physical. Atkins, and what personally I do is that, what personally I'll do here is that in physical chemistry, I'll depend more on numericals, and I will collect different numericals from the different materials. And that's what I do, because concept is 50% and application is 50% in physical chemistry. However, you are good at concept, even you are unable to apply that concept, it is no way useful to you. So organic chemistry, there are so many books are there. Peter Sykes for mechanism you can follow. Right. Only the advanced, the mechanisms are very, very important, and GOC is very, very important. Okay. Right. Now, most of the people have given, a correct answer. That is, suppose imagine this is one hydrogen atom. This R I am taking, and here hydrogen atom is present. This is a nucleus. Okay. And another hydrogen atom is present at infinite distance. Imagine it is present at infinite distance. When this hydrogen atom is approaching this first hydrogen atom, there is a decrease in potential energy. And whatever decrease, the lowest potential energy that we find here is, this will be called as the bond energy. This is the amount of energy released when this hydrogen atom approaching this hydrogen atom. And this hydrogen atom will come to a place where the attractions and repulsions are equal to each other. This is a place it is stable present. Now this is called as internuclear distance. This is called as internuclear distance, or we will call it as a bond length. Okay. At this bond length, both attractions and repulsions are existing there. You know that this is the hydrogen atom. Between the nuclei of two hydrogen atoms, there are repulsions are present. And between the electrons, also repulsions are present. It means two repulsion forces are there. And what are the attraction forces? This nucleus can attract this nucleus. And this nucleus can attract the electrons present here, and this nucleus can attract the electrons present here. So two attraction forces will be there, and two repulsion forces will be there between the atoms. And they will come to a place where both attractions and repulsions are balancing with each other. Okay. So this is a place, this is a point where two atoms are existing in an equilibrium, where attraction forces are balanced by the repulsion forces. Okay. So that's a point that you should always mention. Chemical bond formation is an exothermic reaction there. Okay. Coming to the carbon dioxide here, that okay. I'll teach you some concepts that you can follow. See, we have done so much of work in this that we have created our own methods of explaining the things there. See, suppose in carbon dioxide, imagine that you see what I'm doing. Alpha 1. Alpha 1 is nothing but, listen carefully, that see, have patience and listen carefully. Alpha 1 is the total number of valence electrons present in carbon dioxide. Okay, how many valence electrons are there? 4 in carbon, 6 in each oxygen, totally 12 plus 4, 16 electrons are present here, right? Then alpha 2 is that, according to the LDS, I am talking about only LDS. What is LDS, sir? The electron valency theory is there, which was proposed by Covalency as well as the Lewis. Everybody knows this. Lewis has studied more about the covalent bonding. Covalency has studied more about the ionic bonding. See, this LDS, Lewis dot structures, is the only primary idea about the bonding taking place in some of the molecules. It is not 100% correct, and we cannot apply this LDS to every species. Suppose odd electron species are there, we can't apply LDS there. Where there is an expansion of the octet is there, LDS cannot be applied there. But I am starting with LDS only, and I will reach to that place explaining every structure. You see, alpha 2 EC, I am taking only LDS according to the Lewis there. I am following only LDS. It is something like that. In the exams, they are asking you that, what is the formal charge according to the LDS? Then we are sure to follow only LDS only. Exact formal charge may be different, but according to the LDS, what is the formal charge we should have? Okay, suppose it is something like that. If anybody asking that according to VBT, what is the bond angle in CH4? If anybody asking you, According to VBT, what is the bond angle in CH4? Now we know it is 109 degrees 28 minutes, but answer will be only 90 degrees because according to VBT, bond angle is 90 degrees only. There is no hybridization involved in valence bond theory. If they are not giving VBT, simply they are asking what is the bond angle in CH4, 100% will say 109 degrees. So pertaining to that theory, if they are asking the question, then we should answer according to only according to that. Okay. Right. As far as carbon dioxide is concerned, that alpha 1 is the total number of valence electrons. How many valence electrons are there? Here we have got 20 valence electrons are there. Okay. Sorry. This is right. So 16 electrons are there. What is alpha 2? Alpha 2 is the number of electrons that we should suppose to have around each atom. How many atoms are there? We have got 3 atoms. 3 into 8. See, take 8 for all the atoms except for hydrogen. Hydrogen should have only 2 electrons around it. It should get the duplet, not octet there. So 24 electrons here. Okay. Now we have to magnify the 16 electrons into 24 electrons, right? Why we should magnify into 24 electrons? Because each atom should have the 8 electrons around it. Okay. Now for that, what we need to do? For that, we need to share the electrons because when you are counting it 2 times. Now what is the difference? Alpha 3 is nothing but C right? See, alpha 3 is nothing but alpha 2 minus alpha 1. What is the difference here? That is 24 minus 16, that will be equal to 8. Then alpha 3 prime is equal to 8 by 2. This will give you bond pairs. It means this structure should have 4 bond pairs compulsorily. Without 4 bond pairs, you cannot create LDS. Without 4 bond pairs, you cannot create LDS for carbon dioxide. It will tell you how many bond pairs are possible in this structure. Now alpha 4 is equal to alpha 1 minus alpha 3. What I am doing, alpha 1 minus alpha 3 is, alpha 1 is a valence electrons, alpha 3 is the electrons consumed in the bonding there. So that will be equal to, you will have 16 minus 8, this will be equal to 8. Now alpha 4 prime will be equal to 8 by 2 is equal to 4 lone pairs here. It means what I'm trying to tell here is that without having the 4 bond pairs and 4 lone pairs, we cannot satisfy the LDS for the carbon dioxide. Okay. So you should have 4 bond pairs, 4 lone pairs. It means with this formula, we'll come to know the how many bond pairs and how many lone pairs are essential to write the LDS for this structure we have come to know. Okay. Now imagine for carbon dioxide, if I'm writing the structure like this, oxygen and oxygen, and I'll put the double bond, 4 bond pairs I'm putting. I'm not just writing according to the valency. Keep in your mind, I'm not following any valency rules. My motto is only to give 8 electrons for each atom. That's all. We are in the primary concept of the bonding according to the LDS I am writing. No valency is known, no maximum covalency rule is known, nothing is known. Okay. Primarily, our idea is that around every atom, we should have the 8 electrons, right? Now, 8 electrons are present here. How many bond lone pairs are present according to this 8 lone pairs? I'm giving like this. Why? Because around the carbon, 8 electrons are there. Around oxygen, I need 4 more. I have just arranged 2 lone pairs, here 2 lone pairs. Now, every atom is happy, isn't it? Every atom is happy with 8 electrons. But there is one more probability is that these bonds can be like this also. And that's what we are calling as the resonance. Resonance is nothing but if a species can be expressed in more than one form of structures, and they are called resonance canonical structures, and this phenomenon is called as a resonance there. So only in resonance that electrons are moving, atoms are not moving. You know that basic rule. Now this oxygen will have how many electrons? 2 electrons. This oxygen will have how many electrons? 6 electrons. Now still every atom is satisfied with the 8 electrons. Now I am explaining in the point of view of the students there. To the students, when you are doing a primary idea, our motto is that every atom should get 8 electrons around it according to the LDS. That's all I am doing. I am not following any valency rules, and even I don't know electronegativity also. What I mean to say, students do not know what is electronegativity, what is valency, nothing. My motto is only to give 8 electrons, right? Now, this can also be written like this, 3 bonds here and 1 bond here. Now, this time, this is one possibility here. Okay. Now, if anybody say that oxygen, carbon, we can write like this also. This is one possibility. And you have got electrons. Now, total 4 bond pairs, 4 lone pairs. I am using only those valency electrons present in the 3 atoms. That's all. No extra electron. Now, this can be rearranged like this. If I put like this. This is also satisfying. Every atom has got 8 electrons. Again, I am telling you, my motto is only to give 8 electrons around each atom. Okay. Right. Because octet rule, what is octet rule? Everybody knows that every atom wants 8 electrons in its valence shell. Just like noble gases, in order to get the stability, to get sharing of electrons or by transfer of electrons. Number of electrons shared is called as covalency, and number of electron transferred is called as electrovalency. Okay. And the bond formed due to sharing of electrons is called as covalent bond, and the bond formed due to transfer of electrons is called as the ionic bond or electrovalent bond. Okay. Now, this is one possibility. I can also write one more possibility. The triple bond can be present here. These are the electrons like this. Now the question here is that if you have all the 6 possibilities for the carbon dioxide structure, which one to be followed? How do you judge the structure given in every book is correct? Or how do you convince the students that we should always write the carbon dioxide structure like this? Okay. Then here comes the energy and stress can be known from the formal charge concept. Try to understand. We are getting to know about the stability of these species from a concept called formal charge. One by one concepts I'm introducing into this. Initially, my motto was only to give 8 electrons around each atom. That's all. Now there are so many options. Now the doubt is that which structure to be taken, and carbon dioxide prefers which structure in which it wants to be. Then comes a new concept, that is formal charge. Based on the formal charge, we can say that which structure is stable, which structure is unstable. Now you'll ask me, sir, what is formal charge? Many of you might be knowing that, okay? Don't feel offended that anything which you know I am telling that. Because for the sequence, we have to touch everything. Formal charge is nothing but it gives the account of the electrons when atom is moving from the non-bonding state to the bonding state. It is something like that. Imagine all these 3 atoms are entering into a business, and each atom is investing its valency electrons into this chemical bonding. What for? To get a benefit. What benefit they are getting? They are getting extra stability in the form of a molecule. That is why they are going for this business, to get extra stability. Imagine carbon is investing 4 electrons, oxygen is investing, each oxygen is investing 6 electrons. But once they have invested their valence electrons into the bonding, because nobody knows, according to electron valence theory given by Covalency and Lewis, valence electrons are responsible for the chemical bonding. Okay, primary idea I'm talking about. Only valence electrons are involved in chemical bond formation. We are moving step by step. Okay, don't say that even sir, penultimate cell electrons. See, I am talking in student point of view, that student does not know anything, only knows electron valency theory given by Covalency and Lewis. He knows only what is the definition of chemical bonding. Chemical bonding is a force of attraction between 2 atoms or ions, that's all. And it's an exothermic process, okay? Now, total the 16 electrons are now distributed among them such that every atom gets 8 electrons. This is the broad idea, isn't it? This is an idea. But during this distribution of electrons, one atom may be at loss, one atom may be at gain. Means some atoms are getting extra electrons, some atoms are losing their electrons. This is what happening. It is like a socialism. See, everybody is giving their money and it is being equally shared among the all people, just like a socialism. So we are trying to socialize. Socialism we are following it. And every atom is getting 8 electrons. But because of the socialism, all atoms may not be happy. Sometimes some atoms are losing electrons, some atoms are gaining electrons there. And the situation will be happier situation where atoms are neither losing more nor gaining more, but still they are getting stability because of the chemical bonding. And that we will know through the formal charge. How much they are benefited, how much they are at loss, that is called as formal charge. Formal charge is nothing but simply how many electrons are lost or gained in chemical bond formation. Suppose you imagine formal charge is equal to, we'll say it's valence electrons minus half of the bond pair electrons plus lone pair electrons. Right? Suppose for this oxygen, if you take, for this oxygen, what is the formal charge? It is investing how many electrons? 6 electrons are being invested minus half of the bond pair of electrons belongs to this, because this is a common property between carbon and oxygen. So from this we are getting 2 and plus. Here this lone pairs completely belongs to oxygen only. How many are there? Minus 6 is equal to 0. Okay. Now what is the formal charge here? The formal charge on the oxygen is 0. Similarly, for carbon, orally you can calculate 4 electrons it is investing. No lone pairs are present. How many electrons are there around carbon? Out of this 4, 2 belongs to this. Out of 4, 2 belongs to this. Formal charge is 0. For this oxygen is also 0. So formal charges are 0, 0, 0. Now very fast for oxygen, tell me what is the formal charge? This will be +1. And this will be -1, and this is 0. And don't forget that some of the formal charges will be must be equal to the charge present on the total species. Here it is a neutral molecule, that is where sum of the formal charges must be equal to 0. Now here this will be -1, this will be 0, and this will be +1. I think you can follow this, and you most of you know this also. Now for oxygen, I come into these structures. Oxygen is forming 2 bonds, 0. For this oxygen, it should form only 2 bonds, but it is forming 4 bonds. So +2, and this is -2. Carbon should form 4 bonds, but it's forming only 2 bonds. Even by using the formula also, you'll get the same thing. Now for this oxygen, again, +2. And here for oxygen, what you'll get? This oxygen will be +1, and this will be -3. Okay. For this oxygen, again +2. For this carbon, it's forming 3 bonds. -1, it is forming -1. You can see that some of the formal charges will be equal to the 0 because it is a neutral molecule, right? Now, the more formal charge, the more charge is accumulated in any species, that become more unstable. See, why I'm giving this, because everybody knows the stable structure of the carbon dioxide. If they're asking you in IITJEE, because they are known for asking such questions, they'll create questions, they won't follow any books there. If they're asking what is the most unstable structure possible for carbon dioxide, see, we all know that stable structure carbon dioxide because it is being given in the books, and we have been studying this from our childhood. There, most unstable structure for the carbon dioxide would be that one which is having the highest formal charge, and this will be the most unstable structure. I don't think that they won't ask you this, because if you know instability, you know about the stability there. Obviously, the most stable structure for this is equal to this one. This is the most stable one. This is the most unstable structure for the carbon dioxide possible there. And of course, carbon dioxide prefers to exist in this form and not existing in this form there. Right? So the game is always stability and energy, always in chemistry. I hope you understood that. If they're asking, see, they go beyond the conventional methods. What is appearing in the books, they won't ask you, even in the advanced examination. If they're asking the most unstable structure possible for the carbon dioxide, it is also possible to be asked. That will come to know through this formal charge concept. First, I have introduced LDS to you. Then I have to know which is more stable and which is more unstable. This is the most unstable form. This is the most stable form. I am not following any valency rules. I am not following any covalency or electrovalency, nothing. My main motto is that every atom should get 8 electrons around it, and with lowest possible formal charge, and that will give the stability. So carbon dioxide structure, we are all following since ages, this one only. Which one? Carbon dioxide structure, we are writing like that only because of this reason. That's what we have to convey to the students, that is, stability plays an important role in every chemical process is happening, because always atoms wants to move from the less stability to the more stability. That is what reactions are happening. That is why chemical bonding is happening there. So living, non-living, everything in the nature are moving from the lower stability to the higher stability, or from higher energy to the lower energy. Lesser the energy, more is the stability. Right. Now you may ask, sir, how you are telling that this is most unstable? Because keep in your mind, in organic chemistry also, this concept is very, very every species. Charge is a burden on every species. That is the reason every species wants to get rid of this charge somehow. That is the reason nucleophiles, electrophiles are attacking on the organic compounds, and chemical reactions are happening. Otherwise, the reactions would have not taken place there. Right? So what I'm trying to tell here is that charge is a burden on every species. So to get rid of this charge, everything is happening in chemistry. Let it be chemical bonding, let it be chemical reaction, anything. It is happening to get stability, extra stability, that's all. That is a main important motto. Against this, nothing will happen. If it is happening, it will result in the formation of an explosive there. Suppose chemical bond formation is always exothermic, giving more stability species. Suppose ozone formation is there. Ozone formation is an endothermic process, and that is the reason ozone is highly unstable. Wherever such reverse things, it is not that they're not happening there. Okay. Now, coming to this, taking this concept into competitive exams, what I'm trying to tell you, okay, this concept, always see, my motto is that 50% is concept, 50% is application there. If you are good in concept, it's not sufficient. You should be able to apply this also. Suppose imagine how to apply this concept to the different questions in the exams there, in mains and in advance, what type of questions they are going to ask you. Let us see. I'm giving you one question here, X, then this is F. Fluorine is there. On fluorine, the electron pairs are also given. Okay. And this is the there are 2 electrons. This X is an atom. Fluorine is an atom. This X is also an atom. Okay. Now, three lone pairs are there. Okay. This is a species given to you. Now he's asking that what is X? X can be what? More than one possibility is also there. Don't stick to the 4 options concept there. Okay. Now, how many atoms can be present in the place of X? The same, the LDS concept and formal charge concept, I'm converting into a question, right? Can anybody take the notebook and get me the answers, please? Fast. No. Amit Sahu. Very good, Amit Sahu. Very good. Very good. Very fast answer, right? See, it takes some time to understand each other because I don't know that from which background you are, what is going on in your mind. It takes some time to understand. That is the reason I'm giving some questions. Very good. Very good. Amit Sahu has given a correct answer. Any other answers? Right. Good, Amitji. Now you see, the rule here is that the sum of the formal charges must be equal to 0 because it is a neutral species. No charge is being given. Now, what is the formal charge on this nitrogen? Can anybody tell here that? Very fast, if we calculate, nitrogen when forming 3 bonds, no formal charge, but it's forming 4th bond, it will get the +1 charge. So I'm doing it orally. Suppose you are slow in this, you can do like this. Half of the minus from this I am taking up minus half of the 8. That will be equal to +1 because no lone pair is present. For this fluorine, how much? Fluorine, how much you are getting the formal charge? For this fluorine, it is 0 again. You can calculate, right? We don't know. What's the formal charge of this one? V, valency electrons, we don't know, but it will be 6 + 1. For this one, Valency we don't know. 4 plus 2. Why? Because half of the bond pair of electrons, total lone pairs have taken. This is V minus 6, this is V minus 7, isn't it? V minus 6, it is V minus 7. So I am writing here that V minus 6 plus V minus 7 plus 1 is equal to 0. Sum of the formal charges. 0 plus 1, V minus 6, V minus. It is equal to, how much you'll get? We are going to get it as the 2V is equal to, this is 13, 13 plus 1, 12. This is 12. So V is equal to 6 here. Now the valency electrons are 6 present only in this species. That is why in place of the X, oxygen must be present there. So this is how we can convert a concept into a question, right? So in this, so many things are there. Calculating the formal charges are there, and also you should know. Right. Now, if you take the species like this, carbonate is present, carbon dioxide is present, or you take NO3 minus is present. You see oxides and oxyanions of the second period elements I am taking. Carbonate is there, carbon dioxide is there, nitrate is there. Okay. This is belonging to fourth group, fifth group, right? Third group, CbO3 minus 3 is present. When you take any of these species, what we find is that, suppose imagine there is a special case, I'll take in carbonate, CO3 minus 2, I'm taking CO3 minus 2. And how do you write the LDS for carbonate? See, now the concept is every time we cannot write all the structures and find out which one is the most stable structure in that, right? Suppose there is a situation where you have to write down directly the most stable structure. What are the rules to be followed to write down the most stable structure directly? See, why I have selected these species, because the second period elements behave differently when compared to the third period elements. First will make perfect about second period elements among the students. The students will be convenient with the second period elements because there are no vacanted d orbitals, no expansion of the octet is possible in this species. According to the maximum covalency rule, please write down this maximum covalency rule. For second period elements, maximum covalency is only 4. There is no case where more than 4 bonds are formed by this second period elements. Right? Third and fourth period elements, S and P block only I'm talking about, can form a maximum of 6 bonds. They can extend their coordination up to 6. They can extend covalency up to 6. Right? Second, third and fourth. Fifth and sixth period elements can have a maximum covalency of up to 8. Okay. So this is the second period. They cannot have more than 4 bonds. Site electrons are compulsorily around it. That is why. Okay. So maximum covalency rule says that second period, what's the maximum covalency? Is only 4. Third and fourth, 6. Fifth and sixth period elements can go up to 8. This is a possibility. This is called maximum covalency rule. Okay, I'm telling you, this is maximum covalency rule. Okay, this is a rule, but why we will understand it. Suppose imagine carbonate is present here. Okay, for carbonate, I want to write down directly the most stable LDS. Then if you want to write down the most stable LDS, you have to first choose the least electronegative atom as a central atom. Sir, why like that? When you take the least electronegative atom as a central atom, there is a possibility of getting the lowest formal charges. If you take the reverse, suppose if you put the oxygen at the center here, still you can satisfy 8 electrons around each atom. But again, all the different cases you have to see. Directly, if you want to write the most stable species, select the least electronegative atom as a central atom there. But remember, hydrogen should be never taken as a central atom. Hydrogen is always an exceptional case because of its small size. Though in ammonia, NH3 is there, hydrogen is less electronegative than the nitrogen. Will you take hydrogen as a central atom? No. This hydrogen is exception for many cases. In many cases, hydrogen has got exceptions. One of these exceptions is that hydrogen will never act as a central atom, though it is having the less electronegativity. In HF, which is a central atom, you should take fluorine, not hydrogen. In ammonia, which is a central atom, nitrogen, not hydrogen. Because of its small size, hydrogen should be never taken as a central atom. Otherwise, in all remaining cases, least electronegative one should be taken as one. Central atom should have, what are the three characters? Central atom should have three characters. Number one, lowest electronegativity should be there. Number two, maximum number of bonds. Maximum number of bonds it should form. And it should be connected to all atoms. Connected to all atoms. So if it is unicentral atom, unicentral species, lowest electronegativity you should see, it should have maximum number of bonds. Count the bonds. Whichever is forming maximum number of bonds, you take it as a central atom. Suppose the structure is given to you, right? So connected to all atoms, that one which is connected to all atoms should be considered as a central atom. So central atom should have all these three characters, then only we can call it as a central atom. Okay, right. Now in carbonate, I am directly writing the most stable species. So I have taken the carbon, oxygen, oxygen to the possible extent symmetrical structure we will take. Okay. Again, alpha 1, alpha 2, alpha 3, alpha 4, if you do, alpha 1 is how much? Alpha 1 is equal to 4. 4 plus, now 6, 3, 18, 18 plus 2, because minus 2 indicates 2 extra electrons are present. How much you got? 24 electrons I got. What is alpha 2? Alpha 2 is equal to total number of atoms, 4 into 8, because no hydrogen is present, 32 electrons. I have to expand this 24 electrons into 32. So alpha 3 will be equal to how much? 32 minus 24. That will be equal to how much? 8. Now alpha 3 prime will be equal to 8 by 2 is equal to 4 bond pairs you are going to get. Now alpha 4 is equal to alpha 2 minus alpha 1. Alpha 2 is equal, see, alpha 3, alpha 1 minus alpha, because what are the total electrons? Alpha 1 minus, sorry, alpha 1 minus alpha 3. Total valence electrons are 24, minus out of them 8 are gone for bonding. Then how many are left over? 24 minus 8, 16 electrons. And alpha 4 prime is equal to 16 by 2. So 8 lone pairs. So this will give you a quick idea that how many bond pairs and how many lone pairs are possible to be present in this species there. Otherwise, if you are keep on going for trial and error method, it takes more time and you may go wrong. 4 bond pairs and 8 lone pairs. Is it correct? Right? Now, where do you put these 4 bond pairs? Wherever you want, you can put, because all of them are oxygens only, like this I'm writing. Lone pairs. See, oxygen needs how many electrons more? It needs 4 more electrons. This needs 6 more electrons. And this needs 6 more electrons. Total, how many lone pairs are there? 6 plus 3 plus 3, 6, 6 plus 2, 8 lone pairs. See, total 24 electrons have oriented like this. This is going to give you the most stable structure, right? Now, what is the charge present on this species? The charge present on this species is -2, right? Now, what are the formal charges? 0, -1, -1, it is 0. The sum of the formal charges -1 and -1 gives rise to the -1 gives rise to the 2. And this is, they're called as oxyanions. They're called as oxyanions. Oxyanions are, they're called as acid radicals. Okay. in this acid radicals, resonance is possible, right? Resonance is possible in the sense, what I'm trying to tell here is that this double bond position is keep changing. How this double bond position is keep changing there? Suppose here I wrote O minus, and this can be written as C double bond O minus. This can be written as C double bond O minus. So this many possibilities are there for this carbonate ion, CO3 minus 2 ion. This many possibilities are there. Now there comes an idea that when resonance is present, what is a bond order in this species? Means CO bond order. If they're asking what is a CO bond order in this species, right? How many bond order is nothing but what? Number of bonds present between two atoms is called as bond order. What I'm trying to tell you is that what is the bond order, CO bond order in this species? Come on, please send me the answers. Please send me the answers. First, no time NO2F exists, sir. Is NO2F exists, sir? Yes, NO2F is possible. Right, tell me what is a bond order. I'll tell you one trick that in resonance structures, in oxyanions, then bond order will be equal to 1 plus pi bonds by sigma bonds. Simple thing. Where resonance is there, if resonance is there, suppose if you take any species, 1 plus, how many pi bonds are there? 1. Out of this 4, 1 is pi bond, 3 are sigma bonds. This will be equal to 1.33. The bond order in this is 1.33. The reason is that, see, there are some people who would like to do like this also. Select any bond. They are selecting this bond. And 1 plus 2 by all the structures. 4 by 3. Between two atoms, select all the number of bonds and divide it with the total number of resonance canonical structures. That is also giving you 1.33 only. Whatever may be the concept, but whether you follow like this, I think this is a very simple thing that you can do. Bond order is equal to 1 plus pi bonds by sigma bond. That will give you the bond order. It means the bond order between carbon and oxygen is in between 1 and 2. It is neither completely single bond nor completely a double bond. That is why we have started expressing the carbonate ion like this, because this is minus 2. Okay. So we are introducing resonance formal charges into the LDS here, because LDS is the primary idea. So many changes we have to brought depending on the situation. Now they are asking you that what is a formal charge present on each oxygen? Here it comes. A very, very important thing. That very, very important. That is according to, please listen carefully. Kindly, please listen to me. That according to LDS, what are the formal charges and oxygen? Carbon according to LDS, -1, 0, 0. Okay. Carbon, oxygen. How many oxygens are there? Oxygen. One carbon is 0. Oxygen is -1. This is 0. This is the situation. Right? This is according to LDS. Please keep in your mind that according to LDS, what are the formal charges? Your answer is C, -1, 0. But if they're simply asking you, not using the word LDS, what are the formal charges present on oxygen atoms? Then it will be -2 by 3 This will be minus 2 by 3, minus 2 by 3. Because this negative charge is equally uniformly distributed among all the 3 oxygen atoms there. Among all the 3 oxygen atoms there. Here, so carbon is still 0, oxygen, oxygen, oxygen. It will be minus 2 by 3, minus 2 by 3. When we should give that answer? Here, bond orders according to LS. Bond order according to LS 1, 1, 2, 1, 1, 2. But here, original bond order is 1.33. According to LS, formal charges on carbon 0, oxygen minus 1, oxygen minus 1, another oxygen is 0. But what is reality? The reality is something is different. In reality, carbon 0, each oxygen has got minus 2 by 3, bond order is 1.33. So this resonance concept is led into the different formal charges and different bond orders there. We started with the 8 electrons around each atom. But in order to get, see why all these things are happening. There's only one reason behind it, to get extra stability, that's all. Only to get extra stability, this is all happening there. See, species are all there. There's a possibility of resonance, it is going for resonance because resonance is giving it extra stability. That where there is no possibility, it is not going for any resonance there. There is a possibility. So because of this resonance, it is getting extra stability because it is increasing its bond order 1.33 for everything. So this is happening when there is a resonance is existing there. Okay. Suppose imagine that there is a situation. Okay, I'll select this. Sulfate is present. Phosphate is present. PO4 minus 3 is present. I am selecting, you see central atom is belonging to third period here. Sulfate, phosphate, such species I am taking there. Sulfate is there, phosphate is there. Okay. Why I don't know, the chart is always getting invisible. Okay. Suppose sulfate is there, phosphate is there. Yes, central atom belongs to what? Central atom is belonging to the third period. This is third period. And this is also belonging to the third period species. Okay. Now let us take phosphate. PO4 minus 3. Again, let us write the most stable LDS for phosphate here. What is the most stable LDS for phosphate that you are going to get? Phosphorus is less electronegative atom. That is why I'm writing at the center. Okay, oxygen, 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 oxygen. 4 oxygens I'm writing like this. Okay, tell me how many bond pairs and how many lone pairs are possible in this species according to alpha 1, alpha 2 concept. According to alpha 1, alpha 2 concept, here it is 5, 5 plus 3, 8. 8 plus, each oxygen has got 6 electrons. 6 4 ja 24. 32 electrons we have got. Now alpha 2. What is alpha 2? Alpha 2 means 5 into 8. 40. Now alpha 3 is equal to 40 minus 32. What you'll get? 8. Alpha 3 prime is equal to 8 by 2 is equal to 4 bond pairs. Alpha 4 is equal to alpha 1 minus alpha 3. What is alpha 1? 32. Alpha 3 is 8. Now how much you get? 24 electrons. Then this alpha 4 prime is equal to 24 by 2 is equal to 12 lone pairs. It means this species will have how many bond pairs and how many lone pairs? 4 bond pairs and 12 lone pairs compulsorily. So without this, you cannot create the LDS. Okay. So let us write 4 bond pairs and 12 lone pairs. Where do you put the 4 bond pairs? One is here, one is here, one. Compulsorily, minimum 1 bond must be present there. Right? That is the reason I am writing here. Okay, it is -3. Now, each oxygen needs 6 more electrons. Like this. So total 4 12 lone pairs are present here. This is the LDS that we are creating. According to the Lewis dot structure, LDS structure is for phosphate. But is it reality? Or phosphate is existing like this? Is a question. Okay. Now again, formal charge helps us that why we are moving into the multiple bonds. The multiple bonds are resulted, or we are giving multiple bonds in order to satisfy the lower formal charges. You see, I'll tell you. Now, what is the formal charge on this? -1, -1, and -1, and this is -1. Then, obviously, it will be +1. Why? Because some of the formal charges must be equal to the charge present there. -1, -1, -1, +1, that will be equal to -3. But the central atom always will be in search of reducing its formal charge. So in order to reduce its formal charge, what is this is doing? Against to the LDS concept. This is not according to the LDS. Against to the LDS I am talking about. It is going for a multiple bonds. Suppose it is forming one double bond with this. Whoa, whoa, whoa. Now with this, what is happening for phosphorus? You see. Now count what is the phosphorus formal charge. Anybody? Formal charge on the phosphorus now it is equal to 5 minus. Out of 10 electrons, you take only half of that. No lone pairs. 5 minus 5. 0 formal charge it is getting. This is 0 again. This is -1. This is -1. This is -1. So it is forming multiple bonds in order to reduce its formal charge. This was given by Lewis, but reality is this one. Why it is happening? It is happening because phosphorus wants to reduce its formal charge. That is why it is forming one double bond. You may ask that it can form double bond with this also, but that will give us +1. So -1 it will give you. So it is wants to be at 0. That is only one double bond it is forming here. Now, when the double bond is coming into scene, what happens? This will result into the resonance there, right? This is resulting into the resonance. So many resonance canonical structures are possible for this. How many resonance canonical structures are possible for this? 4 combination 2. 4 combination 3, because the negative charge is present on the 3 oxygens. 4 combination 3. How many structures will get? 4 combination 3, how much will get? 4 factorial by 4 factorial by 4 minus 3 factorial into 3 factorial. This is giving rise to the 4. So it is giving rise to 4 structures. 4 resonance canonical structures. 4 factorial means 1 into 2 into 3 into 4. 4 minus 3. That's 1. 3 is 1 into 2 into 3. Only left over is 4. So this is equal to 4. 4 resonance canonical structure. Without writing directly, we can tell the resonance canonical structure. You may ask, how, sir? 4 is the total number of oxygens. This you should take as the number of oxygens. This is the charges. Okay, so oxygens and charges, to take the 4 combination 3, you are going to get the number of resonance. Without writing, I can tell 4 combination 3, it will give you 4 resonance canonical structures, right? Now, the idea here is that what is the bond order in this phosphate? Bond order in the phosphate. Again, use the concept 1 plus pi by sigma. Now 1 plus, how many pi bonds are there? 1. 1 by 4. This is equal to 1.25. Even if you write all the resonance canonical structures and count the bonds between P and O in one place, then you are going to get 2 plus 1 plus 1 plus 1 by 4. This will be equal to 5 by 4 equal to 1.25. That is also same thing. In one structure, double bond will be there. In another structure, single bond, single bond, single bond only. So bond order is equal to 1.25 in this species. Whereas according to the earliest, bond order is 1, 1, 1, 1 only. But originally the bond order is 1.25. So why it is moving? Because it is increasing its bond order, bond energy is increasing, and it is getting the lower formal charge. Only because of this multiple bonds, this is happening. This transformation is happening in order to get the extra stability there. It is only hypothetical that the idea, the main primary idea is every atom gets 8 electrons around it. But they're going beyond it. See, octet rule is not a rule to be followed by every species. It may or may not be. So this is giving rise to the, okay. Now if they're asking, what is the original formal charge? See, formal charge according to LDS, if they're asking -1, -1, -1, -1, +1. But even original formal charge is not this, -1, -1. The original formal charges will be, if they're asking, according to LDS, if they're asking, give that. What you will give? -1, -1, -1, +1. But if they are asking formal charge in the phosphate, what will be formal charge in the phosphate? Phosphate formal charge. This is -3. The position of double bond is keep moving. It is delocalized. The pi electrons are delocalized on all the 3 oxygen atoms. Hence, it will be 3 by 4. Hence, it will be 3 by 4. 3 by 4. 3 by 4. So, on all the 4 oxygen atoms, same formal charge is present, that is -3 by 4 is distributed. And what is on the oxygen, the formal charge, it is equal to 0. The central atom is happy now. So always the bonding is taking place by the central atom. So first thing is central atom should be happy. The central atom is happy with the formal charge. So according to the LDS, P, O, 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 O. According to the LDS, what were the formal charges that we have seen here? +1, -1, -1, -1. +1, -1, -1, -1, -1. But in reality, what is reality here? In reality, the formal charges are 0, -3 by 4, minus 3/4. This is the reality. So according to LDS, PO bond order is equal to 1. But reality, what is experimentally reality in the sense? Experimentally calculated value, experimentally found value is 1.25. 1. So the expansion in octet is happening in the third period elements onwards because there is a possibility of expansion as they have the vacant d orbitals. But as far as second period elements are concerned, there is no possibility of the expansion because there are no vacant d orbitals are present in that. Okay. So I hope that we are going in a sequence, right? See, after this class, please, if you have any doubts, you can send your doubts to the WhatsApp number given, already provided to you. Okay. So my request is that I hope to the extent of my knowledge, whatever I've explained, that you understood this. So if you have any doubts, please WhatsApp, and what you want me to discuss also you can send to this number. So only send message. Yeah, move to organic. Yes, we will do in sequence because we have a lot of time. So everything we have to discuss. If you want me to discuss organic, we will do that also. But we have a schedule. According to that schedule, we will be following, and that schedule will be finalized according to your wish only. So please WhatsApp and send message to this number. Any doubts are there, any queries are there, or any request is there that you want me to discuss about a particular topic, then I send only messages to this number, and accordingly we will act on that. So thank you, friends. I hope that you understood what we have discussed in today. And the continuation, see, even for organic chemistry also, chemical bonding is very, very important because in GOC, chemical bonding plays a vital role. Okay. So what we have discussed in today's class is that I started with a simple question that why a structure of carbon dioxide or any structure should be written only like that. Why we should not give a different structure like this. For carbon dioxide, the structure is finalized based on its stability, and that stability is known from the formal charges. We have seen what is formal charge, and we have taken some species where central atom belonging to the second period. In second period, compulsorily octet rule is obeyed because there is no choice for them. They have got only p orbitals and s orbital. There is no d orbital. That is why octet rule is followed. But octet expansions are observed. Of course, octet contraction is also there. We'll discuss about that. Octet expansions are observed where central atom is belonging to the third period, right? So we have taken the examples of sulfate, phosphate. So many examples we have taken here. Take some species. Miesler is a book where you will find so many species. Okay. And from those species, you try to write down. I'll give you some questions to solve. So we will be discussing different methods, different shortcut methods in different topics. See, I'm giving you some questions here. SnF3, SOCl2, write LDS for this. POF3, SOF4, SO3F minus. This is a work you try to do. And also CNO minus and SCNC minus. Thiocyanate, cyanate, these are also very important. Okay. Please try to write down the LDS for this species and find out the formal charge in this species and find out which is most stable, which is unstable, or directly write down the most stable species, right? So I'll stop here. Friends, thank you very much for listening to me, and we'll meet you again in the next session. Thank you. Bye.